Hey everyone, in this lesson, it's almost like a part two of our last lesson. We're going to be approximating discrete distributions with the normal distribution. And today we're going to look at how to do that for the hypergeometric distribution. So let's get started. It's a bit of a warm-up. Last day you were introduced to this idea of the continuity correction because the normal distribution is a continuous distribution. But often things that involve discrete data follows a normal distribution as well. And we'd like to be able to tie the two together. So for example, we got this warm-up question. Scientists are measuring the number of words our group of monkeys can understand. And the monkeys could understand an average of 45 words with a standard deviation of 7 words. And we're going to assume the data is normally distributed. So for these first two questions, I'd just like you guys to see if you can draw a diagram, a normal distribution diagram that represents the problem you're trying to solve. Maybe shade in the area that you're looking at and apply the continuity correction. So when you're doing less than or equal to 42 words, what's your range of values going to be? How are you going to handle that? And same with greater than 40 words. So if you want to pause the video and unpause when you're ready, you can do that. Or you can follow along with me right now. So just do a rough sketch here. So the mean is 45. 45. If you were finding the probability that a monkey recognizes less than or equal to 42 words, so it's a less than prob, you'd be finding this area. But remember, when we're taking discrete problems and using the normal distribution, we apply this continuity correction. And we treat 42 as a range of values between 41.5 and 42.5. And if we want to include 42, that means we're going to go up to 42.5. And as I mentioned last lesson, whether you use 42 or 42.5, it doesn't make a large difference in your answer, but it makes a difference. How about the next one? Greater than 40 words. So it'd be something like so. But what value is your cutoff value? Well, it's greater than 40. So we're not including 40. 40 is 39.5 to 40.5 as a range of values. And we are not including that. We just want greater than 40, which means our lowest cutoff is 40.5. And that's how you would solve those problems. One last one. This one, I'd like you guys to solve it completely. So can you apply the continuity correction and solve the problem? So if you'd like to go ahead and pause the video, solve the problem, come back. And I should say these warm-up questions are not on your lesson sheet. So just you can just scratch them out on some rough paper. So the mean was 45. And just our standard deviation was 7. So 35 and 49. So 35 somewhere down here, 49 a bit closer. We're finding this interval here. Now we are including 35 and 49. So 35 is 34.5 to 35.5. We want to include that. 49 is 48.5 to 49.5. We want to include that. So now we've turned this problem into a pretty normal distribution problem. Pardon my dad joke there. So you guys should be pretty well equipped to do these now. So I'm just going to find these z-scores. 7. So that's negative 1/2. And 49.5. 0.64. So the probability that our value is between 35.5 and 49.5 is equal to the probability of these z-scores being between negative 1.5 and 0.64. And we look up those corresponding z-score probabilities from our table. And because it's a between question, we'll subtract them. So 0.64, 0.7389, and negative 1.5, 0.0668. And we've got it. So if you did all that, good for you. If you applied the continuity correction, that's great. If you didn't apply the continuity correction correctly, maybe you did 30, if you did 35 to 49, you'd be a little bit off. So 0.6721 or 67.21%. Just one small thing about the continuity correction. If you weren't to use it, let's say you use 35 and 49. That gives you a range of values. 49 minus 35, that's 14. It gives you an interval that would be 14. This area would be 14 units wide. But look what we have here by using the continuity correction, 49.5 minus 30.5, that's 15 units. And actually, 35 to 49, you can count it out yourself. That's 15 numbers. So applying the continuity correction is really actually makes this question, our answer, more accurate, because by applying the correction, we have 15 values. If you don't apply the correction, you're only really taking 14. So pretty important. All right, so last lesson, we saw that if you did enough trials, that the binomial distribution kind of looked normal. Well, the same thing is true with the hypergeometric distribution. So I'm going to, let's just say for argument's sake, let's say that n was 100 and we had, say, 75 people in our success group. And you picked a group of them and you wanted to see the number of successes, right? So what would happen would be you're going to get a skewed distribution. You're going to get, for the most part, higher values in your group being successes. But then you'll have this possibility of not a lot, but because the ratio of A over N is 75% of the values are successes, you get a lot of successes, but it'll tail off. But if you have a large enough population, you can kind of see you can possibly fit a normal distribution curve here. It's not perfect, but it is possible to approximate it. Now, the condition so what does large enough mean? So in this case, the condition is that and I might just, for this one, let's say R was 10. So then you might expect 7.5, and then you might get, there's 8, 9, 10. But you took a group of 10, it is definitely possible that you might get 4, 3, 2, or 1, right? It just tails off. So here I use 10 and 100. Would that be big enough? Well, here's the condition. The sample size has to be less than 1/10 of the population. And that's the condition we use. So why do we use that one? Well, that's for mathematicians doing more complex stuff than us to decide. But that's it. The group size has to be less than 1/10 of the population. What happens if you actually make your group size bigger than that, then the normal distribution curve gets skewed and pulled out, and it actually doesn't look normal anymore. It looks skewed. But by making the sample size smaller, it gets closer to being normal. So that's your condition. If you recall with the binomial distribution, we had to check that NP was bigger than 5 and NQ is bigger than 5. Here, this is what you got to check. If that check holds up, to turn this into a normal distribution problem, we need a mean and standard deviation. Well, we know the mean. The mean is the expected value, which is RA over N. And the standard deviation, and you guys, you know nothing good is coming when you see a huge square root sign. This formula derivation is way beyond the scope of this course, so we just are going to be able to use it. So you do the root of R times A over N times N minus A over N times N minus R over N minus 1. Now, depending on for those of you guys that have a textbook, or depending on any resource you might use outside of like this lesson here, there is another way to express that. And it's this: NPQ NP minus N over NP minus 1. Now, the people that have a textbook, this is actually the version that's in the textbook. I find it confusing because you guys are used to working with R, A, and N, and then the formula here changes things up on you. In this formula, they're assuming that NP is the number of things in your population. So they're using NP for N. And they're using, instead of R for the number of the sample size, they're using little n for the sample size, like a sample population. So instead of N minus R here, they're using NP and N. It's just a variable choice. N on the bottom here, NP, and then R and N, and then P is your kind of like our confidence intervals. P is actually like your ratio of success, which is, of the N objects, A are successes, and that's where the P comes from. And of your N objects, the remainder, N minus A, are failures. So everything kind of lines up with the above formula. I like to use this one, and I like to teach that one because my students are used to using R, A, and N. So in the example we do next, we'll use that. So we're gonna just do one problem today because you guys did the bulk of the learning in your last lesson with the continuity correction. So we're gonna solve this problem two ways. We're going to determine the probability that exactly 4 girls are chosen using the hypergeometric distribution. We're going to see how accurate we are, and also have a little talk about why this could be useful. So we have, in a grade 12 class, 75 boys, 150 girls, so 225 in total. Now we are looking for the probability that girls are chosen. So in this case, we're considering girls to be a success, 150, and we are choosing 10 at random, so R equals 10. So probability that exactly 4 girls are chosen. So this is a good little review of discrete distributions. On the bottom, the number of ways to choose 10 people, 225, choose 10. On the top, number of ways to choose your successes, 150, choose 4. And the number of ways to choose your failures, well, there's 75 boys left, adding to 225, and we have to choose 6 of them. So I'll do that. You guys do it too. Choose 4 times 75, choose 6, divided by 225, choose 10. All right, so I got 0.055. or 5.5%. All right, so let's see how this approximation does. And we'll go through our list of things to do. So remember, first we have to actually check, hey, is it okay to use the approximation? So let's calculate, well, let's just say, so R is 10. So is 10 less than 1/10 of the population, which was 225. 1/10 of 225 is 22.5. So yeah, 10 is definitely less than 22.5. So our condition, the sample size, is less than 1/10 of the population. 1/10 of the population is 200. Well, the population is 225. 1/10 of that is 22.5. So as long as our R value is under 22.5, we can use the approximation. So we're good. Second step, if we want to turn this into a normal distribution problem, we have to find our mean and standard deviation. So RA over N, R is 10, successes was 150, N was 225. 1,500 divided by 225. 6.67, let's say. And the standard deviation, we got to calculate this big mess. So R is 10. Success ratio, 150 over 225. Failure ratio, 75 over 225. Times population size, 225. Minus sample size, 10. Over population size minus 1. All right, so you may want to do that in a couple steps. To be honest, I'm going to do it in a couple steps. 10 times, I'm going to do all the top stuff. 10 times 150 times 75 times, that'd be 215. And that gives me 24,187,500. I suppose I could have done this all in one step, but it's just a lot. 225 times 225 times 224 on the bottom. 113 or 11,340,000. All right, and I'll divide those two guys. 24,187,500 divided by 11,340. And square root the results. I get a standard deviation of about 1.46. All right, now we're ready to solve the problem and apply our continuity correction. So we're trying to find the probability that exactly 4 girls are chosen, but we have to apply our correction. So we're finding the probability that when we're treating 4, why is that negative? 4 is a range of values between 3.5 and 4.5. So we're finding the probability that our random variable is between 3.5 and 4.5. And that corresponds to their z-scores being between, well, we have to find the z-scores. So z 3.5, the z-score for 4.5. So you guys have your mean and standard deviation over here. So find the z-scores. I'm going to do that really quickly. So both are below the mean, so they'll both be negative. 7 divided by 1.46. So we get a z-score of negative 2.17. And then 4.5 minus 6.67 divided by 1.46. And negative 1.49. And you guys are old hats at this now. Find those two probabilities and subtract. So negative 2.17, 0.0150. That is the one I'll be subtracting. So 0.0150. And negative 1.49, 0.0681, 0.00681. No, 0.0681. Nope, that's good. And then subtract. Minus 0.015. I get 0.0531 or 5.31%. All right. Now, if we compare that with what we got earlier, we got 5.5%. So 5.3% seems pretty good. I have a little table here comparing. Well, it says 0.049. So I wonder if I did something wrong. I'll check that in a second. But we got this one using the formula, and then the normal approximation doesn't do too bad. And actually, this table shows for all 11 possibilities what you would get using the hypergeometric and what you would get using the normal. And then they're plotted on this graph here. And you can see they actually line up pretty good. So let's just have a quick look here and make sure that see if I did something wrong. So R is 10, A is 150, and N is 225. That seems okay. Okay, 10 times 150 times 75 times 215 divided by 225 squared divided by 224 and root. Okay, 1.46. Maybe my z-scores are off. So 3.5 minus 6.67, and then divided by 1.46, negative 2.17. That's good. And negative 1.49 negative. 4.5 minus 6.67 divided by 1.46, negative 1.49. So those are okay. I wonder, negative 1.49, 0.0681, negative 2.17, 0.0150. Okay, well, I can't find what I did wrong. Maybe you at home did. If you find it and want to send me an email, that'd be great. Because I think when I've done this before in the past, I have matched them up, but I'm wondering why I didn't get them matched up here. Anyway, maybe you guys can dig and find that out. But our solution looks pretty good. And the nuts and bolts of how to do it is the same. You got to do your check. After that, you find the mean and you find the standard deviation using the formulas. And then you apply the continuity correction and solve the problem like we normally do with normal distributions. All right. It might even just be a rounding thing, perhaps, like we rounded this, we rounded this. What you guys would be expected to do is take a problem where you might have to use the hypergeometric distribution. Now, this question we did was actually more practical to do just by using the normal or the hypergeometric distribution, because it's just a one value. You just do the formula, get an answer. Instead, though, if we had turned and said, well, what if we had to do the probability, say that the number of girls was less than 5? Now, would you want to do 4 hypergeometric calculations and add them up? Or would you rather do one normal distribution calculation after setting it up a little bit? It depends. It depends on what's more work. I can tell you if our R value was a lot bigger, and we did this kind of question, like a less than or greater than question, if instead of doing 10 or 50 or 100 hypergeometric calculations, we'd much rather convert it to a normal problem and solve it that way. So just a reminder, setting problems up using Z-scores, it can be a bit of a grind. And if you know what you're doing, you don't always just have to just use your table. Like if you get how to use your table, make use of a normal distribution calculator. So I've already linked this one in a previous lesson. But if you just Google, this link doesn't work because it's an image. But just Google Wolfram Alpha normal distribution probability calculator. You get something like this, and you can just, if you put in your mean and standard deviation, you can just put in like, okay, I want the range of values between 3.5 and 4.5, and it spits out your answer. Here's another one as well. This one you pump in your mean standard deviation, and it gives you the option. Are you doing a between question, a less than question, or greater than question? And it kind of shows you how the answer comes up. I thought that one was pretty good. I just checked the link. It does still work, even though this is from an older lesson. Or maybe you found one like on your phone or some app that works just as well. I'm sure there's one. There are those out there. But yeah, I mean, just to say, like, if you know what you're doing, if you want to save some time, you don't need to use your table all the time. You can start using technology to do things quickly and efficiently. All right. So from the same practice as your previous lesson, you're now doing some hypergeometric questions. So R2, R4, 2, 4, and 5 are hypergeometric questions. 11 and 12 are some application questions. And I'm just going to leave those for you and have you guys decide, is this a question where I would apply the binomial distribution or hypergeometric distribution? Because, yesterday was obviously all binomial. Today, obviously hypergeometric, but I wanted to give you guys a couple where you have to choose which is which. All right, that's it for this lesson. I hope you guys are staying well. We'll see you soon.